Hey everyone, welcome back to another science and technology video with Miss Hinkson. So what are we doing? We have moved into the Earth and Space part of the program, and that section is, that unit, I should say, is separated into three sections: astronomical phenomena, general characteristics of the Earth, and geological phenomena. We are going to be studying each of these sections separately. Term one, we'll be looking at astronomical phenomena. In term two, we'll be looking at general characteristics of the Earth. And term three, we will be looking at the geological phenomena. But we are starting with the astronomical phenomena. So the stuff that we're going to be covering in this video today, the content can be found in textbook pages 348 to 355. So when you finish this video, I am going to ask that you read those pages. So as I mentioned, we are starting with astronomical phenomena. And I always tell you it's a good idea to go in the dictionary and see how words are defined. Most of you know what astronomy is affiliated with, but I'm sure you do not know how to define it. So the dictionary says astronomy is science that encompasses the study of all extraterrestrial objects and phenomena. So we were talking about this word extraterrestrial. Some of you guys were like, oh, Miss ET, which is very true. But what does extraterrestrial mean? Can we break apart this word and try to understand what it means? So, again, we're trying to define astronomy. A lot of you guys said, Miss Astronomy, you said stars, you said the moon, you said stuff that basically go beyond Earth, right? So, over here, if we look at the word extraterrestrial, your knowledge of Latin based languages such as Italian and French might help you understand what this word means. The word extra, ask yourself, what does that mean? If I ask you to do extra work, if someone's personality is extra, what does that mean? So, extra basically means to go beyond, right? So, it's beyond or more. What do we see here? If I ask you to look at this piece here, what is that? We see the word terre, right? Which is earth. So extra earth, or we could say beyond earth. So astronomy is science that studies things that are beyond this earth. And some of the phenomena that happen beyond this earth actually does affect earth. And we will see that later on. Okay, so what, sorry, sorry, look at that, sorry. What will we be learning in the astronomical phenomena section? We will explore the solar system. We will study several natural phenomena, such as the succession of day and night, the cycle of the seasons, the phases of the moon. By studying eclipses, the appearance of comets, polar auroras, and meteoroid showers, you will also be able to explain the more uncommon events that frightened our ancestors. So back in the days, there were a lot of things that people couldn't explain, and they said it was spooky, or it was maybe the gods or the spirits and stuff like that. And now, with the advancement in technology and advancement of science, we are able to discover what these things really are. So, we are going to be starting our studies in the astronomical um, phenomena area. Sorry, we're going to be looking at light. I think it's important to start with light because a lot of the astronomical phenomena that we see actually involves light. So there's a lot of things where we feel like our eyes are playing tricks on us, and light is responsible for these things. So this is how we're going to start our investigation. So I'll ask you to take a moment before we actually go into looking at what the textbooks and all the literature say about light. I'll ask you to take a moment to reflect and think about what light means to you. What do you think about when you hear the word light? What kind of things pop into your head? Maybe for me, I think about I need light to see. If it's totally dark and there's an absence of light, I can't see anything. So take about 5 seconds and think about what light means to you or how you would define light. So I looked at three different sources, which include encyclopedias and dictionaries, and this is how they defined light. Light is electromagnetic radiation that can be detected by the human eye. Light is the brightness that comes from the sun, fire, etc., and from electrical devices, and that allows things to be seen. The third one, light is a form of energy. So, in science, we always talk about properties, right? The characteristics of things. So, here are some very popular properties of light. It can be natural or artificial origin, meaning where it starts, where it comes from. The sun is the main source of natural light on the earth. Artificial sources include light bulbs, neon lights, TVs, computer, iPad screens. So anything that gives you light that's not the sun and is created by man is an artificial source of light. So, how does light behave? No, I don't mean is it bad or is it good? Does it need a detention? I just mean how does it work? How does it travel? What are the predictable things about light that we know or we think we know? So, one thing that we do know is when light hits an object, either some of the light is reflected or some light is absorbed. Okay? How much light is absorbed and how much is reflected? It'll really depend on the type of surface it comes in contact with. And also it depends on the color. Is the object dark or light? When an object absorbs light, it absorbs energy and heats up. So some of you guys may remember your parents saying you're going out on a hot summer's day and you're putting on a black t-shirt or a dark t-shirt and your parents are like, "Are you crazy? You're going to burn up in that dark shirt." Well, that's called the black body effect. And you can read more about the black body effect on page 352 in your textbook. Basically, what it is that dark colors absorb light. So when the sun is shining down, the dark colors will absorb the light and there will be radiation and heat. You'll feel that heat. So the light energy turns into this kind of heat energy. When you are wearing white, the light is reflected off of your clothing. So you don't feel that heat as if you were wearing black. So on page 352 of your textbook, it says, don't wear a black t shirt. What happens when light hits an opaque obstacle? All opaque objects reflect some of the light and hits them. The light that hits them, sorry. They absorb the rest. Okay, so we're going to learn about opaque and stuff shortly, but let me read that again. All opaque objects reflect some of the light that hits them. They absorb the rest. Dark colored objects reflect little light, so they don't reflect a lot of light. They absorb most of it. They usually give off the absorbed energy in the form of heat. We call this phenomenon the black body effect. It explains why in summer you feel hotter when you wear dark clothes. You will also notice that asphalt becomes very hot in full sun. This phenomenon also explains why dark objects are difficult to see at night. Light color objects reflect most of the light that hits them. They absorb little light and therefore transform little of it into heat. So you are to see figure 64 in your textbook. Again, that's page 352. And then it goes on to say, oh, actually, you know what? We will look at that later. So let's just go on to the next slide. Oopsie, oops. Alrighty. So this is basically talking about the black body effect. Okay, so the light's coming in, right? So that's the incident light, or the light that's coming in, the light that's shining. Some of the light is absorbed, right? Some of it is transmitted, and some of it is reflected. But when you have a dark surface, it absorbs most of the light, okay? And only a little bit is transmitted or passed through, and only a little bit of it is reflected. Okay, so that explains why you go into a store and when it's spring and summer, the color of the clothing is really, really light. That's because the spring and summer, the sun is shining, the temperature's hot. You want to keep as cool as possible. So you want to wear colors that will reflect most of the light as opposed to absorbing it. Then we get to fall and winter when it gets colder. So when that sun hits down on us, we want to be wearing a color that will absorb the light and give off some heat, right? So it keeps us warmer. So, exactly what happens when light encounters an obstacle? I'll ask you to think about what an obstacle is. So, basically, an obstacle is something that's in the way of something, right? So, what happens when the light encounters something in its way, right? So, light likes to travel in a straight line. Well, that's what, this is what we think. Light likes to travel in a straight line, but when something gets in its way, it behaves differently depending on what gets in its way. So we're over here. When light encounters an obstacle, basically three things can happen. First situation, the light can go through the obstacle almost completely. So that means almost perfect transmission. It goes right through the object or the obstacle. Second situation, the light can go through only partially. So that would mean some of the light rays pass through. Third, what the obstacle that it comes encounter to can stop all the light rays from passing through. Okay, so what happens depends on if the surface of the obstacle is transparent, translucent, or opaque. So over here we have our light source, right? In this case, it is a flashlight. So the first scenario is the obstacle is transparent. So we see here are the light rays that are coming in to contact with the surface, and all of the light rays pass through. That's what makes a surface transparent. So what that means is because all of the light has passed through, I can see what's on the other side of this obstacle. It is transparent. I can totally see everything that's on the other side. Clear as day. The second situation is when your obstacle is translucent. So as you can see here, we have all these rays coming in, right? So these are the light rays, but only some of the light passes through. What is the product of that? Well, when you have a translucent surface and not all of the light passes through, you can kind of see what's on the other side, but not fully. Sometimes it looks blurry, or you just can't really tell all of the fine details. So that is a translucent surface. Now, when we have an opaque surface, all you see here, these are all the light rays that are coming in. Do we see any on the other side? Nope, because an opaque surface will block the light from going through. So, what does that mean in terms of seeing what's on the other side? We can't see what's on the other side. So, this is a summary of what we just spoke about. These three people are holding up three different types of surfaces or obstacles, I should say. The first one is holding up a transparent obstacle. Transparent objects allow all of the light to pass through them. This means we can clearly see through them. The second situation here, translucent. Translucent translucent objects only allow some light to pass through them. This means that we can partially see through them. So here we can see that there is someone on the other side, but we can't perfectly see like this one. Then we have opaque. Opaque objects do not allow any light to pass through them. This means that we cannot see through them at all. So can you think of some examples of transparent, translucent, and opaque objects? So in page 351 in your textbook, it summarizes the idea of opaque, transparent, and translucent surfaces or objects. The obstacle is opaque, meaning nothing can be seen through it. For example, a person, a mirror, or a brick. In this case, light does not pass through at all. It is blocked by the obstacle. A shadow is formed behind this obstacle. Situation number 2, the obstacle is transparent, meaning it can be seen through. For example, glass, air, water. In this case, light goes through the obstacle almost completely. Third situation, the obstacle is translucent, meaning that the light passes through it, but what is on the other side cannot be seen. For example, wax paper, a thin cloth. In this case, the light goes through the obstacle only partially, a certain amount is absorbed. So when we look at this, translucent is basically like an in-between point of opaque and transparent. So you start off transparent, you can totally see what's inside, what's on the other side. And as you progress, and less light rays go through, then it becomes translucent. And then when no light rays can go through a surface, it's opaque. So page 351 depicts these situations, I should say, of transparent, opaque, and translucent. So there are 3 different objects or 3 different obstacles. Here is your light source. In transparent, we see that the light goes through. So we have 2 light rays leaving here, and they go through the object. And these dashed lines signify that this is behind the object. Okay, so this is showing us that this is going through the object. In the opaque, we see that the 2 light rays are not allowed to go through the surface. Okay, in the third situation over here, we can see that it's a little bit blurry. Oh, sorry, let me go back. Okay, translucent. We have 2 light rays partially going through, and some of it is not allowed to go through. Okay. So again, on page 351 in your textbook, you have a summary of all of this in table form. So table 10, how light behaves when it hits different surfaces. So this column, discusses the type of surface. This says what happens in terms of absorption. And this talks about reflection. So we're going to look at the first row. Opaque surface. Okay, so we're talking about opaque, but then we got to look at what happens when they're different colors. So opaque, remember what opaque is like, you can't see through it. So when it's rough and dark, for example, like a black wall, in terms of absorption, these surfaces absorb most of the light. They give off absorbed light in another form of energy, for example, heat. Now we're still looking at an opaque, rough and dark surface. What happens in terms of reflection? These surfaces reflect a small amount of light in multiple directions, dispersion of light. Okay, now let's look at opaque, but let's look and see what happens when the surface is smooth or pale, for example, like a white wall or a mirror. So what happens in terms of absorption? These surfaces absorb a small amount of light. What happens in regards to reflection? These surfaces reflect most of the light. Now let's move on to a transparent surface. Transparent surfaces, light goes through these surfaces almost completely. Okay. Reflection. These surfaces reflect a small amount of light. Now, what happens when your surface is translucent? Light goes through these surfaces only partially. A certain amount is absorbed. These surfaces reflect some of the light. Okay, so let's talk about tinted windows. Usually, when we talk about reflection of light, absorption, and the black body effect, students normally ask, Miss, are tinted windows, do tinted windows have anything to do with these concepts? And they are right. Tinted windows are a topic that should be covered by this material. So, why do people tint their car windows? So, I've asked my students this. And one student said to me in my last class, Miss, because it looks nice. And that is true. Okay. Once upon a time, they created a tint for a certain reason, right? And it wasn't for the car to look nice. But then people saw, oh my gosh, this looks really nice. And then people started tinting their cars just for aesthetic purposes, just to make their cars look nice. But what is it really for? Well, tinted windows give a certain level of privacy. So you've ever seen stars or the president, and they have these cars that are tinted so dark you can't see inside at all. It's almost as if the windows are opaque. All right. So for privacy. And the third reason keeps the interior of the car cooler. So before we go on to discuss the theory behind this, I'm going to ask you to think about these things. How do tinted windows work? How do they give you privacy? How do tinted windows keep the interior of the car cooler? So I want you to think about what we talked about in terms of translucent, transparent, opaque, absorption, and reflection. Okay, so think about those things and think about how they relate to a tinted car. Have you thought about it? All right, so how do tinted windows work? Okay, so here we're gonna just have this really simple image of a tinted window, right? So it's this little skinny rectangle. This represents a tinted window. So here's the glass, and this is the tinting film, right? So that's what gives it that darker look. And here is the sunlight. Okay, so here are sunlight rays coming in. Here we see some of the visible light, that's what VL stands for, some of the light is reflected. Okay. And then some of the light is absorbed by the tint, which is a dark color. Remember, dark, opaque, dark surfaces absorb light. And then some light passes through. So it gives you privacy because of the darker color. Not all the light passes through. So remember, when something is translucent and not all the light passes through, we can see some of what's behind the obstacle, but not everything. Okay? How come it keeps the car cooler? Well, because not all of the light rays are going into the car. Some of the light is reflected, some of the light is absorbed, and only some of the light is going through the car. So remember, we discussed how the sun rays, when they hit a certain surface, they give off the energy is converted into heat sometimes. So if not a lot of the light is coming into the car, then it is actually avoiding that heating process. Okay, so here we see this picture that this company is showing you their tints that they have available. And over here shows you percentage of light transmission, meaning how much light it allows to come in the car. So a 50% tint, right? Let's say that somewhere in between there is a 50% tint. So it lets in half the light, and then the other half of the light is either reflected or absorbed by the tint. So as we see here, the percent transmission is decreasing. That means it's lowering the amount of light that's allowed to pass through. So over here with a very heavy tint, a dark tint, only 5% of the light is allowed to go through the window. Keep in mind that in Quebec, we have tint laws where we're not allowed to tint our cars super dark because of that privacy reason, meaning the tint gives you privacy so people can't see in. But for law enforcement purposes, the police feel like the cars should not be too tinted so that they can see who's driving the cars or what's happening in the cars. So remember, we have laws in Quebec, and that's why you won't see those very, 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 very dark tints on the front and the back because they're not allowed. You are allowed to tint your back windows darker, but they want the front windows lighter so that they can see who's in the car. So now it is time for you to think. It is trivia time. It's time for you to see if you've absorbed any of the information that we were learning or if it reflected, meaning you didn't absorb it and you don't remember the stuff. Alrighty, so in this trivia, we are discussing translucent, transparent, or opaque. So I want you to examine these three pictures and tell me which figure is depicting translucence, transparency, or opacity, or opaque. So which surface is opaque? Which surface is transparent? Which surface is translucent? So I will give you a couple of seconds to think about that. All right. So in this first picture, what's happening? We have light rays that are coming in. And what's happening? Are they allowed to go to the other side? Are some going to the other side? No. All the light rays are stopped by the obstacle. They do not pass through. None of them pass through. So this is an opaque surface. What's happening in this one? Okay. Some of the light rays are passing through. Okay. And going in different directions. This light ray has been totally stopped. Okay. So not all of the light is being passed through. Not all of the light is allowed to pass through. So this means that this is a translucent surface. Next, we see all of the light rays are passed through. So this means it's transparent. So I will be able to see what's on the other side. This one here, translucent, I can kind of see what's on the other side, but it's going to be distorted or blurry. And over here, I totally can't see what's on the other side. All right, so here are the answers: opaque, translucent, and transparent. Next question. So we have a giraffe behind this thing, right? So you have to tell me which one of these is translucent, transparent, or opaque. Okay, so remember, how do we know when something's translucent, transparent, or opaque? If it's opaque, we totally can't see what's on the other side. If it's transparent, we can fully see what's on the other side because all of the light passed through. If it's translucent, we can kind of see what's on the other side, but it's a little bit blurry or a little bit faint. Okay, so translucent would be this one because we can see what's on the other side, but not fully. Transparent would be this one. Opaque would be this one because we totally can't see what's on the other side. All right, so here we have some objects, 3 different columns. You are to decide which column represents opaque, which column represents translucent, and which column represents transparent. I will give you a second to think about that. Alrighty, let's look at the first one. We have things like a window, water, and this see-through glass. So if we put something on the other side, we can see what's on the other side. Like look at the window, we can see the sky or whatever that is on the other side. We can see through the fishbowl. So this column must represent transparent. Over here, we have things like milk, a banana, an 8-ball, a red cup, and dice. If we put something on the other side of these things, would we be able to see what was on the other side? No. So that means that this column represents opaque. Over here, we have a picture of iced tea, a stained glass, and this you can't see, but this was a old school Mac, I believe, and it was relatively kind of see-through on the side. So because we can kind of see what's on the other side, but not fully, this column represents translucent. All right, so here are some more interesting facts about light. Okay, light mostly travels in a straight line. There are some exceptions, but that's beyond the scope of this course. You'll look at that when you get into higher levels of science. The speed of light is around 300,000 kilometers per second. That is super fast. Some of your cars, the fastest your car can go is 300 kilometers per hour. So think about that in comparison to this. Light is actually waves of electromagnetism, part of the electromagnetic spectrum. Only this part can be detected by our eyes. So this is something where you don't really have to know that much about how the waves work. You will learn about that again if you take higher science courses. All right. So refraction is another way that light behaves. Refraction is light bending as it passes through one medium to another. So over here, we can see that the light is coming in and it's coming into contact with this glass body or this glass object. So what happens is as it comes from air and goes into another type of medium or another type of substance, the light bends. That's because it's going really fast in the air. And when it comes into contact with something else that's more dense, like this glass, it slows it down. And that slowing down causes it to bend. And then here we see the light coming out of this object and it's bent again because it went through here and it was slowed down and then it goes through air again and it bends. Okay, so refraction is light bending as it passes from one medium to another. Okay, so these are other examples of refraction. You've seen a straw in a glass and it almost looks like it's cut. Okay, so these things are things you've seen in textbooks or in real life. Natural light, such as sunlight, contains all the colors of the rainbow. we pronounce this, so it's an acronym for all the colors of the rainbow, and people often spell it out and say it like a word, Roijibiv, so that they remember the colors, and it's always in this order. Okay, so natural light can be separated into all those colors. Here we see the triangular prism, and that is white light was passed through a prism and it's glass and it bent. And on the other side, we see all the colors that white light is composed of. So we are going to read pages 352 to 353. So page 353 shows this image and discusses it. So I'm on page 352 in your textbook, and I'm in the section that says the secrets of white light. Sunlight is white. Artificial white light also exists. Many people believe that white light is colorless and that something must be added to it to color it. What do you think? Do you think that shining a beam of white light through a red filter will color it red? Well, you're wrong. In 1666, Isaac Newton showed that white light was in fact a mixture of different colors. Newton shone a beam of white light through a triangular glass prism. So that's this here. He then observed that the white light separated into several colored beams on the other side. See here. He deduced that the white light's color resulted from a mixture of all of the other colors. Okay, so what I just spoke about is this picture here. So that light that's being shone onto the glass prism symbolizes white light. As it passes through one medium to another, right? Remember, we just spoke about refraction. The light bends, and it bends a certain way so that on the other side we see the colors of the rainbow. And it's always in this order, Roy G. Biv. Okay, it always goes red, orange, yellow, green, blue, indigo, and violet, and you'll see why after. But that is always the way that a rainbow will manifest, with the colors in this order, and you can see it here. Okay, how many of you guys have been walking on the street and seen like it looks like you have a rainbow on the ground, right? So that is another trick or another thing that light does. And when the gasoline mixes with water and then the light hits it, there's a bending going on of the light. There's refraction. So it gives off this rainbow looking type of thing. So again, this is refraction. This is the Prism experiment that Isaac Newton did to show that white light is actually a mixture of colors. And here again, we see Roy G. Biv. We see the red, we see the orange, we see the yellow, we see the green, we see the blue, we see the indigo, and we see the violet. Roy G. Biv, always. So how is a rainbow formed? Well, you can imagine that it has something to do with refraction as well. So we're going to look at a video.
Surely you've seen a rainbow. Maybe you were chasing tornadoes and happened upon one. But did you ever notice that the sky is darker above a rainbow than below? I never did until someone pointed it out. We're going to find out why this is so with the help of refraction of light, dispersion, and the incomplete story you're usually told about why rainbows form. This story starts with refraction, the bending of light as it moves from one medium, like air, to another medium, like water, at an angle. Light actually slows down in water. Visible light would take 11 minutes instead of the usual 8 to get from the sun to the earth if there were a giant ocean in between. So as light slows down when it enters water, the beam is forced to turn. pattern. But unlike the constant speed of light in a vacuum, the speed of light in water depends on the color. Violet light moves slower in water than red light, so it will bend more as it enters the water. An incoming beam of white light will be spread out and separated into a spectrum of color. We call this dispersion. Now let's take this white light beam and send it through a droplet of water. Some of the light will refract into the droplet, then reflect off the back and refract back out to travel down to your eye, typically at an angle of 42 degrees between the incoming light and the outgoing light. This can occur in a circle of droplets, so if the ground weren't in the way, rainbows would be a full circle. Here's the fun part. Violet light refracts more in the water droplet than red light, as we discussed. So violet light should end up exiting higher in the water droplet than red. But if we look in the sky, red light is clearly higher than violet light. What's going on? Well, if you're observing from down here, this water droplet will only send red light to your eyes, and the violet light will pass above you. It's the droplets down here that send violet light to you, and the violet light will appear to be coming from lower in the sky, as it does. And that's how we get our colors in the rainbow from rain and sun. End of story. But there's one part I never understood. Why should all of the light enter the water droplet right at this point? Well, the answer is it doesn't. Some red rays enter here, some enter here, and they all exit in different directions. If we add back in the other colors, you end up with an exiting, jumbled mess of color. This mess of color should look white, but it definitely doesn't. So what's going on? This is where it gets more complicated than you usually hear. As this red light ray enters higher from the midpoint, it exits at an increasingly large angle. But watch what happens here. Eventually, the ray turns around. No matter where red light enters the droplet, it can't go past this angle. That's the maximum angle, and it's 42 degrees for red light. It's slightly less for orange and yellow and so on until you reach violet, where the max angle is 40 degrees. So it turns out that at that maximum angle, you also get a maximum brightness. So even though all the colors can reach here around violet's max angle, because their maximum is beyond that, violet is at its maximum brightness, so it stands out against the other colors. Same goes for the max of the other colors. Below violet, no colors are at a maximum, so all the colors mix again and form white. That's why the sky appears lighter below the rainbow than above. None of the light can make it out above red, so the sky appears darker. Then how did this second rainbow sneak up there? Well, you'll notice the colors are flipped in order, and again that the sky is lighter above them. That indicates that the light had to reflect twice inside the droplet. In order to get the right angle down to your eye, it actually had to enter the droplet from below the midpoint, and you get a double reflection, causing a second rainbow. Now the story is complete. The end.
All right, so if you just watched that video and you're like, I still have no clue how a rainbow was formed, that is totally fine. It is not something I expect you to fully understand in secondary one. Okay, so we heard about this word, this phrase, I should say, the electromagnetic spectrum. So when we talk about light and we are referring to light, what we're really talking about is the light that we can see, or the visible light, and that's only a small part of the spectrum. All of these other rays are light rays, but we cannot see them. So this is in page 354 of your textbook. It says the electromagnetic spectrum. Again, I'm on page 354 of your textbook. White light is not the only radiation emitted by the sun. It was not until the late 19th century that scientists discovered this phenomenon. They called the range of the sun's energy radiation the electromagnetic spectrum. Okay, so in your textbook, you have a similar image to this one, and it's figure 68. In this spectrum, the human eye perceives only the part called visible light. So over here, that is visible light. But certain insects can see ultraviolet rays. Okay, so the ultraviolet rays are over here. And certain snakes can see infrared rays. Those over there. So in your textbook, table 11 presents each of the different kinds of radiation emitted by the sun. So again, if you do not understand how the electromagnet spectrum works, that is fine. Again, I don't expect you to totally understand this in secondary one. I just want you to know that when we say, oh, we see light, and the light that we see, we're only talking about this little portion of the spectrum that is visible light. Okay, so again, this is the visible spectrum. And what do you notice about the order of the colors of the visible spectrum? There is that Roy G. Biv again. So Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. It's always in that order. So now the question arises, why do we see the colors that we do? Right? So light is white, right? So white light, we see it, it looks white, but then Isaac Newton discovered that it's a mixture of colors, Roy G. Biv. So how do we perceive the colors that we do? Okay, so how do we see colors? We see objects because light from a luminous object reflects off of the object. So luminous, something that's light, that emits light. Okay. Some of the colors of light are absorbed. Only the colors that are not absorbed are reflected and enters our eyes. This is the color we see. Okay, so we will look at that. So here is this white light that's coming in. So we see the Roy G. Biv, right? So it's white light and it's composed of all these colors. And over here, we see that it comes into contact with the surface, and all of these colors are absorbed. And this here is reflected. Okay, so we see some reflection. So based on what is reflected, those are the colors that we see. So here is an example. So a green surface. Why do we see that it's green? Because when the white light is coming in, it absorbs every ray, every color that is not green. So we're talking about something that has a green surface. Why do we see it? So it's almost to say, like, the surface says, oh, I'm gonna eat everything. Oh, except you, green, because I already have you. So it reflects it. So whatever is reflected is what the composition of color of the object is. Okay. So if I did not show you this surface, I didn't tell you what color it was, and I showed you this, the fact that the green light is reflected would tell you the surface has to be green, because the surface will reflect the color that is like its surface. Okay. So again, over here, we have another example. The grass is green. Here is our light source. The white light's coming in, right, with all the different colors here. And all those colors are absorbed except the green, because this is green, so it reflects the same color, right? Because it's like, I don't need you, I'm already green. And it's almost like it spits it back out and it's reflected to your eye. And that's what you see. Here's another example. Your ladybug is red. We have all the colors coming in. These are all absorbed. The surface says, oh, I don't need your red, I'm already red, and reflects the light, the red light, to our eyes. And that's why we see red. All the other colors are absorbed by the surface. Okay? So let's take the time to summarize some of the things that we learned. So we're going to take a look at this video.
Light. It's all around us.
But what is it? Where does it come from? And what does light have to do with color? Light is a kind of energy that travels in waves. It is made when matter is heated up or gains energy. Excess energy is released, in part, as light. This energy is called electromagnetic radiation. When we talk about light, we usually mean visible light, which is the light that we can see with our eyes. But there are more types of electromagnetic radiation that are invisible to us, including radio waves, microwaves, X-rays, and gamma rays. Scientists can detect and measure invisible radiation with special tools. Together with visible light, all these types of radiation are called the electromagnetic spectrum. All electromagnetic radiation travels in waves, but different types have different wavelengths. The wavelength of electromagnetic radiation, or light, is connected to how much energy it has. Light with a longer wavelength, like radio waves, has less energy, while light with a shorter wavelength, like gamma rays, has more energy. Visible light makes up only a tiny part of the electromagnetic spectrum, but it includes every color we can see. The most important source of light here on Earth is the sun. We call ordinary sunlight white light, but it actually includes all the colors of visible light. These colors can be revealed when white light goes through a prism. When light passes through a prism or something like it, it slows down a little bit and bends. Some parts of the light slow more than others, and the light spreads out into the colors of the spectrum. If you want to see all of the colors in the visible light spectrum, look no further than a rainbow. Rainbows are made when water droplets in the air bend sunlight much like a prism. Usually when we talk about a rainbow, we say it is made of 7 colors: red, orange, yellow, green, blue, indigo, and violet. Each color has a different wavelength. Red has the longest wavelength in the spectrum of visible light, and violet has the shortest wavelength. All the other colors have wavelengths in between the two. The colors of a rainbow are always in the same order because the colors are arranged according to their wavelengths. Red is always on the outside because red has the longest wavelength, and violet is always on the inside because violet has the shortest wavelength. Electromagnetic radiation with a wavelength outside the visible light spectrum is invisible to our eyes. Light with a longer wavelength than the reddest red our eyes can see is called infrared light. Light with a shorter wavelength than the most violet we can see is called ultraviolet. When we look at an object, we are actually seeing the light that is bouncing off of it. A green leaf looks green because the leaf absorbs all of the colors in the spectrum except for green, which it reflects. When the green light enters our eyes, our brain tells us it looks green. Things that look white are reflecting almost all of the visible light shining on them, and things that look black are absorbing almost all of the visible light shining on them. Light, both visible and invisible, is all around us. It travels from its source as a wave, bringing energy with it. Without light, there would be no colors. Take a look at the world around you and remember, everything you can see is just different wavelengths of reflected light. Goodbye till next time.
So that was a pretty cool video to kind of summarize some of the things that we saw. So here are some other things that we looked at. And I want you to take time to look at these things and think about what you know about each of these topics. So light, in regards to light, we spoke about reflection. We spoke about light energy. There was this discussion about a prism. We spoke about visible light on the electromagnetic spectrum. We spoke about absorption and refraction. What can you remember about all of these topics? I'll give you some time to think about each one. All right, let's summarize each one of these topics. Reflection. Reflection occurs when light bounces off of an object, example, a mirror. Light energy. Light energy is the only form of energy we can see. So visible light, I should say. Visible light energy is the only form of energy we can see. Light travels in straight lines most of the time. Prism. A prism is a three-dimensional transparent object, plastic or glass, that refracts light. When light passes through a prism, it's separated into different colors. So that was the Isaac Newton experiment that we looked at, where white light was shone onto the prism and it's separated into colors. Can you remember the colors and the acronym and the word that we use to remember them? Roy G. Biv, right? So red, orange, yellow, green, blue, indigo, and violet, Roy G. Biv. Visible light spectrum. The visible light spectrum is the part of the electromagnetic spectrum that is visible to the human eye. And here's that Roy G. Biv again. Absorption. Absorption occurs when light is not reflected or refracted. Example, shining a flashlight at a wall. Okay, so that's like, when something absorbs something. Okay, so reflected, meaning it doesn't bounce off, and refracted, meaning it doesn't go through and bend as it passes through. It's just stopped, right? It's just absorbed. Then we have refraction. Refraction occurs when light bends after contact with new matter. Example, a straw in a glass of water. Another way to define it is light. Refraction is light bending as it passes from one medium to another. So we saw the example of the prism, which was a refraction experiment. Light passing from air into glass or plastic, right? So the light bent as it moved from one medium to another. So I hope now that when I asked you in the beginning to think about light and how you define it and ask yourself what you know about light, I hope now you know a little bit more than when you started this lecture. So I'm asking you to read pages 349 to 354 in your Eureka A textbook. Again, this is another science and technology video with Ms. Hinkson. And if you have any questions, email me at hinksons@loyola.ca. I'd like to thank you for listening and come back again.